good shot in the arm coming back here, just getting excited about my science. So thank you to all of the locals that are here. It's always good to be back. Yeah, this talk is going to be, we're going to start really big at the landscape scale. I'm going to show you how going back down to the molecular scale ultimately helps us understand what's happening up at the field scale. And the M in EMSL stands for molecular, and let's not forget that and remember just how important it is. And I hope to show that to you today. Other thoughts that I wanted to get across before I really got started was that I'm going to be talking about uranium in this talk. And it can be a distraction, maybe the way DOE is going these days as far as their lack of concern or consideration about radioactive elements at this point. But I'd like you to also put forth that what I'm going to show and how we've approached it is just as relevant if instead of looking at uranium, we were looking at a nutrient element or even understanding macronutrients and things like iron oxides and their processes. And so uranium is a wonderful sentinel for things that are happening in the environment. And finally, this talk hopefully I'm in an electron microscopy session, but I'd like to believe, and you'll see that I could have just as easily been in the synchrotron session. And throughout my career, I've embraced taking advantage of all the different techniques and try to get to the answer. And so hopefully what I'm going to do today is tell you a story, keep you entertained, and at least half of you will stay awake while I'm talking. So there's the title, Investigations of Colloids to Understand Field Scale. We know colloids are very small. So let's talk about the field, where we're going out into the field. It's the Savannah River site. That's in Aiken, South Carolina. It is right across the river from Augusta, where they play the Masters golf tournament every year, where there are tons and tons of radioactive waste sitting at the Savannah River site. It's about the size, you can see, oh, there we go, first screw up. Here's its location, actually in Georgia. It looks, in South Carolina, it looks like it's in Georgia. It's about the size of Rhode Island. A lot of enrichment of radioactive materials during the Cold War occurred here. And so something the size of Rhode Island, we've got this little square here encompassing Timms Branch, which I'll talk about in a little while. But you can see something from the early 70s of an aerial view of that area, which we'll go into in a second. But there's this manufacturing plant where they did a lot of this fabrication of the fuels. Fuel targets and whatnot, which we'll talk in a second, and how this all comes together. So from a cartoon perspective, you see in the top there, in the top left, excuse me, there was this M area facility that from 1954 to 1989 was manufacturing nuclear fuel and target assemblies. And being in a DOE national lab, speaking to some of these people that I'll mention later who've got process knowledge of what was going on back then, they described it to me that they were doing this in and out, and then every once in a while the guys would show up in their hazmat suits with fire hoses inside these massive facilities and just hose everything down, goes into a drain, went into a settling basin, which then slowly drained made its way down a rather steep incline to Timms Branch. Then it went down to and got held up in Steed Pond. Steed is named after Farmer Steed, who owned the property before it was the Savannah River site. He dammed up the Timms Branch to have a pond to water his farm animals. And so we've got this 43,000 kilograms of uranium during that time, made its way down Timms Branch into Steed's Pond, settled down into the sediments. And then 1984, the dam ruptured. All went rushing further down. The water went rushing down. And we were left with this flatland area where the pond used to be. And over the years, you had an evolution from, if you will, from a grassy wetland system to a forested wetland system. And what we're defining now is also a riparian system where you've got this small stream making its way through the flat wetland areas, which are constantly flooded with all these sediments that have accepted a variety of heavy metals and uranium through those years, exposed to episodic rain events. So if you live in this part of the country, you know that often in the summer months, almost every afternoon, you get your big thunderstorms. So, big deluge, and this water comes rushing down through this system. And so there was a little bit of a concern about what's happening to that uranium, and that's where some of this work started. They did a study back in the early 90s where they went downstream below Steed's Pond and looked at the movement of the water as a result of that, say, a torrential downpour or a hurricane that may have come through. And they found a strong correlation between when you had that high movement of water through the ecosystem, there was also a high concentration of uranium at the same time. And they could also filter the material. And they also found the filtered, which were called the dissolved uranium components. Dissolved, we're putting that in quotation marks for right now, meaning hydrated. It was stuff that was smaller than 0.2 microns that they filtered it. And so we started a project, I'm going to say 7 years ago, a science focus area with BER, where we wanted to understand how this ecosystem is functioning and how it's controlling the movement of those radioactive and heavy metals through that system, as it possibly makes its way out of the system or makes its way further downstream. And so we felt that the things to focus on to understand that were 3 areas. First, on the left, you can see the sediments. In the middle, representing the stream water, Tim's branch moving down right through that wetland system, and then the rhizosphere. And I'm purposely taking a little bit of time here to hit us all over the head that you can see that we appreciate in our group. Everything you're seeing for the most part is molecular scale processes that we're putting in those cartoons that we believe are the things that we need to understand on the system, understand these molecular processes, and we're going to have a much deeper insight of what's happening and how the ecosystem is functioning. So go back to when I was here back in '97, and I met some of the early great scientists in redox biogeochemistry, John Zachara, Jim Frederickson, Ken Nielsen, lots of others that were here. DOE spent a lot of time trying to understand redox biogeochemistry. And so we immediately, when I talk about a riparian system now, where we've got this cross section of the stream we're seeing here with the wetland system, the groundwater is going to be up comparable to where that stream is. It's a gaining stream. That means the groundwater that's in the sediment is making its way into the stream and it's flowing out. If it's that's a losing stream. If it's a gaining stream, saying it backwards, excuse me. The gaining stream, it's what I just said. If it's a losing stream, the water in the stream would actually go down into the groundwater instead of flowing out. Most of it would be flowing into the ground. But you can imagine in this gaining stream situation, where the groundwater is making its way into the stream, you've got this anoxic groundwater because the microorganisms have consumed the oxygen. They're now respiring on the iron 3 oxides, creating an iron 2 rich environment. We've got the contaminated uranium that's in the system, and we've also got a lot of organic matter. This part of the country is known for iron-rich, organic-rich soils. So this is what's happening here on the anoxic side. The movement of this water now hits this oxic front. There's a reoxidation process occurring, either abiotically or the microorganisms that might be iron oxidizers taking advantage of that electron transfer to gain energy. where you now could have the oxidation of the iron 2 to iron 3, precipitation of new iron minerals. Uranium, we know when it's in a reduced state, is supposed to be highly insoluble. Uranium-4, supposed to be sitting down as a rock, shouldn't even be moving through the groundwater, should be sitting still in the ground. But if it was to get through somehow, it's going to be oxidized on the other side, and now it's highly insoluble. Uranium-6 loves to stick to stuff. Okay, so this is the system, and this is our early understanding of it as we jump into this project and take this ride this afternoon. So what happens is we go from the groundwater into the stream water. So we put a well down on one side. You're going to see these are not very complicated wells. The water's not very deep here. You don't have to go down deep to get to the water. And we're going to gather water from the groundwater from this well, and we're going to gather the stream water. We're going to see what's happening in these two different types of samples. So the way it works is you walk out into the field with a battery pack, small pump. You can see down here in the bottom these little containers backfilled with nitrogen gas in advance, so it's anoxic. Put a needle in it, so when you're pumping the water from the groundwater into these canisters, you're pushing the nitrogen gas out. It's not seeing the oxygen. We're keeping it under anoxic conditions. We do it very slowly. We ensure that the rate at which we're pumping it out is not so fast that the water level's dropping. We're not disturbing the sediments that might be at the bottom of this well. Put that on ice, put it at UPS, and we're going to ship it to Argonne National Lab overnight. Arrives at Argonne less than 24 hours later. We now want to start looking at those particles that might be associated with the water, the colloids. Now, often when people filter water, they say we put the screen up, we push the water through, there's a certain size of the filter, and that's what's being held up. But when you look closely at what really happens, as you're doing this filtration, you will get particles that will start clogging and caking up inside there, and you'll actually reduce the size of the holes. And so your cutoff actually gets smaller as you're filtering, and you do not have a very accurate understanding of what you're getting. But there's another technique called tangential flow filtration. It's illustrated here in this cartoon where you can imagine where the water is moving in this direction. Your particles are up here, but there's a natural pressure that would allow the smaller particles to make their way through. The larger particles, normally they would sit here and they would block the filter. But if you've got a tangential flow of water going this direction, keep flushing them away and getting them out of the way. So you start your water here, you run it through a hose or a straw that's got these pores on the outside, so that as the water is moving through this hollow filter, the smaller particles, smaller than the size of the pores of the straw, they're making their way out, and they come down here and they can be drained away from the system. If it makes it all the way through with the larger particles, it's brought back into your original reservoir. And as you're running this system through, all the water here is being drained out. It's going down here. What's left in this water is got those particles that are larger than your pore. And what gets through are the smaller pores. There are 3 publications I'm putting up here of work that was done back and developed in the late 80s. It was some of the first work done this way. It was not a new technology, but the application to the environment this way it was the first time it was done. I'm highlighting Kent Orlandini in bold here, who was sort of the guy that created all this concept and did it back then. These were landmark pieces of work, saved the Department of Energy literally billions of dollars in cleanup, and also told him where to focus at some of these sites because of colloid transport that he demonstrated, which people said was not possible to be happening. This is a picture of Kent. Started working at the lab in 1957. This is Kent analyzing our samples. And I'll give you a second to do the math. This tells you you are never too old to do science. This man gets in earlier than I do. He's in his 80s, and he sometimes stays later than I do every day. A lot of passion there. Wonderful person. He's sitting in there in our anoxic glove box, taking those samples that were shipped from Savannah River site, and he is doing the tangential flow filtration for those samples, which then just tell you, so the colloidal sizes. So I'm going to mention throughout the talk large, medium, and small. Here are what we're talking about, those sizes. When you get down to these really, really small sizes, you go by molecular weight instead of size. But if you're more comfortable with size, large particles are things that are bigger than 0.1 microns. Medium are 0.3 nanometers, and the small are bigger than 0.1 nanometers. So those samples are then 3/4 of a mile away from our lab, brought down to the advanced photon source. Thank you very much for all the introduction on X-ray absorption spectroscopy. You're going to make my life a lot easier. We're going to do X-ray absorption spectroscopy measurements on some of those samples. First being, let's look at the iron. We told you it was an iron-rich system. We talked about the iron redox biogeochemistry. So on the top left, you can see an iron 2 and an iron 3 Zane standard in the symbols. And you can see the large, medium, and small particles for the groundwater. And you can see they all basically lie on each other, and you're noticing that it's an iron 3. And that was the first surprise. As I told you, the groundwater was reduced groundwater, and we're seeing oxidized iron 3 in a reduced groundwater system. So that's the first part that was interesting. We can look to the extended region of the X-axis, the extended X-ray region, absorption region. You can see overlaying there of just a ferrihydrite for a fingerprinting system, a fingerprinting approach, very similar to ferrihydrite, which is an iron hydroxide, highly amorphous system. And over on the right, you can see a linear combination fits to the different, the 3 different sizes, giving you the percentage of ferrihydrite citrate, which would be an iron associated with organic matter, and then lepidocrosite, which is another type of iron mineral. So what we're finding is these particles that are being filtered out in all sizes are showing us predominantly in a rather amorphous iron hydroxide mineral that's sitting in these very small particles. But the iron is also associated with organic matter. So we're going to remember that. Very quickly, just go through the same thing. Doesn't look like much change. This is now the stream water, basically seeing the same thing. I will point out, we're going to go backwards 1 second for something I forgot to mention. The smallest particles actually have around 40% of an iron organic matter association, where the larger particles were up around 25 or 30%. As we're going to these smaller and smaller particles, we're seeing more and more of the iron associated with the organic matter. So there's something about particle size and association with this organic matter that's going to be relevant. Don't see that as much in the stream water, but again, you see the iron oxides and the organic matter. Now let's come back to EMSL. Let's call my good friend Ravi Dapu. Ravi and I think was one of the first people I met here back in '98 or so, and Mossbauer spectroscopist extraordinaire. They take those materials. Now they're characterizing with iron, Mossbauer, and lo and behold, we're getting basically the same results. So we're feeling pretty confident that tour de force measurements of the synchrotron, tour de force measurements of this very, very small amount of material, it took a lot of time at both facilities to measure. We're getting the same results, organic and this association with iron, as well as the iron hydroxides. But interestingly, well, I'll show you, this is the groundwater. Similar type of result came from the Mossbauer of the stream water. But in both cases, although we agreed with each other, we've got this 10% slop in our results, typical noise. But Mossbauer is also seeing some additional components of iron in the clays and something they're calling nanogertite. And Ravi and I love to have this ongoing debate. Is nanogertite really just ferrihydrite? And just you're using a different word. We think there's a lot of interesting concepts in unifying these two approaches, and we're actually working on including that in the manuscript. Going to publish its results. Now let's jump over and sit on the uranium atoms. That's what we're worried about, what's moving through this system. So here's the zanes of the stream water, all right? The quality of the data. So first off, we can see that the uranium is oxidized. Again, wow, no matter where we go, stream water, groundwater, it's oxidized. So there may be something going on with where the electrons are sitting in this iron organic complex. The electrons are all there. They just might be shifting around within the complex itself. On the right, you're looking at the quality of the uranium excess data. And you're probably saying to yourself, that doesn't look very nice. It looks pretty noisy. But I will tell you the size of the sample was smaller than a pencil. And the concentration of uranium within that pencil point was around 10 parts per million. All right, this is a tour de force measurement that you need an undulator at the advanced photon source to look at. We're basically looking at a laser with about 500 micron size beam to do this bulk spectroscopy. Got a lot of X-rays coming out in that very small spot. Long integration times just to get the quality of this data here. The samples were frozen to make sure radiation damage was not an issue. But you can see the quality of the data. We attempted to fit. You can see over here on the left, the symbols in the x-axis are showing you the data that we collected. And then everything else up and down there are all the different standards. So again, doing a linear combination fit as a first approach to trying to understand what's happening here. We can see that the uranium looks very similar to uranium when it's sorbed to a lepidocrosite or ferrihydrite standards, roughly 50-50. We also went through a variety of standards here, one of them being DFOB, which is a abbreviation for uranium associated with organic matter. But the quality of the fit actually is not as good. There's actually a slight reduction in the quality of the fit. So there's no indication here that this uranium is associated with the organic matter in this very little dot of colloids that we were able to collect from that tangential flow filtration. We can, instead of doing a linear combination fit like this, we can go to PHEF and do a shell-by-shell fitting of the data. What you look at on the top is a standard of uranium in solution, hydrated, with its two axial oxygen atoms sitting around there, and then a belt, the equatorial oxygen atoms surrounding it. And you can see that fit that we get the two axial and the roughly 5 equatorial do a wonderful job of fitting uranium when it's in a hydrated state. That's the top one. Drop down to the middle one, and now we're looking at the uranium when it's sitting in those colloids. And you'll notice that when I put uranium hydrated, it doesn't do a very good job of fitting in this region right here. Put in one iron atom, you see the quality of the fit down below, fits right there, real nice. And then if you take a very simple model of a ferrihydrite, and you take your uranium and you do a bidentate bonding, you'll get something roughly of around 3.44 angstroms as being that distance you expect to be here. So we've got a smoking gun indicating that this uranium is sticking to the iron oxides that are in these colloids in a bidentate type of association. Let's come back to EMSL. All right, so now we've been sitting at the molecular scale. Let's bring it up a little bit. Let's look at the electron microscopy. Here's an SEM image of the stream water colloids in the top left. See what it looks like here. Here's the elemental distributions. This is the frame that's actually holding some of these particles back. That's sitting on the electron microscopy grid. That's the carbon base. So you can see a very strong correlation with what the iron and the oxygen looks like, consistent with the ferrihydrite type of mineral being formed. You also can see a few dots that are right at the noise level of uranium in there, trying to do this image, and some other random elements. So That's cool. It seems like polymers. Again, we've got the carbon. If you look closely, you can see some correlations here, but it doesn't look exactly the same shape-wise compared to the iron image, but you can see this general, low hum of carbon associated with it. So we've got this almost like this carbon coating, we're assuming randomly distributed on these iron oxides. Go to another particle that was shown, and you can see here now it's got a shape. They were calling it ferrihydrite when the information was sent back to us from the electron microscopist. They called it clustered ferrihydrite. Same type of results that we saw earlier, but now if you sort of take this whole general area and take all the images, all the different pixels, sum up all the X-ray fluorescence signals, you can see the uranium fluorescence there. So that's a smoking gun telling us uranium is there. You can pick it up in the fluorescence signal. Point out that we didn't ask for this, but if you look closely, you can actually see a very large peak over here. And if you look behind what was overplotted, it's actually the chromium. If you remember back at the beginning, I talked about all those other heavy metals that were associated with it. Chromium was one of the bad actors associated that came flying down the tube too. So we can see the chromium is also coming along for the ride. We now go to a different electron microscopist at EMSL. And we're zooming in now with HAADF, high annular dark field transmission electron microscopy. And this is something that we did with EMSL decades ago, right when, not decades, a decade or so ago when they first got this there, when we were looking at some nanoparticles of uraninite. And lo and behold, zooming in on this, please, you can actually see these little white dots, which are individual uranium atoms. Yeah, this was the coolest thing. Individual uranium atoms in an electron microscope rib. They're very heavy. They pop. And what you notice is individual uranium atoms peppered throughout this ferrihydrite system. Just like the molecular scale work we did saying individual uranium atom bidentate going to the iron oxide. So we're grabbing this at different length scales, we're putting it all together, and everything is consistent on itself. Okay, well now let's go to even a bigger scale. Back to the Savannah River site. Well, it turns out they've got a big Homeland Security project going on down there. And before every Super Bowl, they take this helicopter and they fly over the Super Bowl. And they got a big old gamma detector on that thing. And they're looking for uranium, other transuranic elements that might be giving off a signal as if a terrorist may have brought a bomb in. So instead of going to the Super Bowl, they took this thing and they flew over Tim's Branch for us. 100-foot apart stripes down. And they gave us, position-wise, where the helicopter was, what was the gamma ray signal. And you can see the what happened? Can you bring me back? Help. I got too excited. Go back about 5, 6 slides, the last 5 or 6 slides. That was all my fault, just to be clear. I can take it from here. Thanks, sorry. So this helicopter does every 100 feet apart, does this strip, measures the intensity of the gamma rays. And it's a little screwed up here. I think there's a problem in the translation, but this square actually sits right up here. And when you're going down here, you can see what they got from the gamma rays. Here's the road. Where is the road? Okay, you've actually got a road running through here. You can see it here. This is where Steed's Pond was. This is where the dam was. And there's actually a higher concentration we found even further up above the pond. So we had this 30-meter resolution. We thought that was really cool. Thank you to NNSA. Then we got the University of Georgia graduate students together. We gave them a gamma ray detector with a GPS, put it in a backpack, and then they walked over a period of 2 days, this army of students with all these things, they walked and mapped out the distribution of the gamma ray intensity on the entire watershed with 1 meter spatial resolution. So now we know right where that uranium is sitting. Here's Steed Pond, here's the road. This is where it ruptured years ago. There's a hot spot down here, but there's a big spot up here. Turns out back even before the dam ruptured, there was a beaver dam right here and created its own little pond. So if we take this image, go to the next slide, and then take all this here, plot it right here, what you start seeing is that here's where the M facility was here. There's a really steep hill going down. You can see the contour lines, very, very steep. The water was rushing very fast here, got into this part here. You can see you've almost got this, you can see the slopes on both sides of these hills, the stream running through where the riparian wetland system is located. This is where the flat area was. Here's where the beaver pond was. Here's where Tim's Branch Seed Pond was located. Okay, so if I go to the next slide, we're now going to plot as we start from the M facility. There's that steep drop off before it entered Tim's Branch. And then it made its way down Tim's Branch to Steed Pond. And this is where we call the deposition areas. That's where the beaver pond was. You'll note, however, that we don't have uniform axes on here. We've got roughly 100 meters in elevation this way, and we've got over 7,000 meters on the x-axis. So, thanks. It looks like a rather steep slope here, but it's pretty flat when you take that over 7,007 meters. So it turns out surface water flow is having a big effect here. And that's how we're going to sort of end this, is that within the groundwater and stream water, the uranium is molecularly associated with these colloids and particles. Where they settle at the ecosystem level is highly dependent upon how fast that water is moving through this thing. You find the very flat areas where water doesn't move very fast, or it can move itself out when there's the heavy torrential downpour. There's just a lot of wide open space for that water to go through. It's not moving in like a rapid or anything like that. So that's where the uranium settles out. So if you think about it, they want to know where that uranium is going downstream. If you go, we're telling them if you go downstream and you go to where all the slowest moving water is, that's where you're going to find this stuff. We don't even have to go look. We know what it is from this. But it wasn't without all these measurements that we've not been able to figure out why this is happening. Because this is not the way uranium would move if it was just associated with the water. It's the colloids and the particles that it's sticking to that determines where it's going to settle. So, acknowledgements. I said at the beginning, it's a great group of people out here, and I've been enjoying it for not quite, but almost 30 years. Always great to be here. Showing the 4 people that were critical in the work that I showed you from EMSL today, as well as collaborators at Argonne, Kent Orlandini since 1957, people in Bulgaria, the Savannah River site, Alice Dolnikova, who has recently left the laboratory. She will be missed. But yeah, a great group of people, and that's what makes science fun. Before I end, you've heard a lot about Eber Light in the last couple of talks. I shouldn't say a lot, but it's been mentioned a few times. It's my job in 2 slides to sort of tell you, to give you the summary of what we want to make sure we get across to you. You heard stuff of what's been happening at SLAC. They've been doing this for quite a few years. This week, Eber Light officially became an official entity. It is a user facility at the Advanced Photon Source. Very similar to what you heard in the description that SLAC gave. Same concept, same type of idea is trying to be put forward there. They have at Argonne, at the Advanced Photon Source, they had these things called CATs, Collaborative Access Teams, or different beam lines that have different types of capabilities. And so what they've done is through this program that's being supported by BER, they basically have ownership in a percentage of a lot of different beamlines throughout the APS. You can see some of them there for crystallography, tomography, microscopy, X-ray absorption spectroscopy, like what I was talking about today, and small angle scattering, plus a lot of other capabilities from the computer computation to handle the data, preparation of your materials. That's all also going on within eBer-Lite. It's there to help people facilitate access to it. The people you'd want to know about, Karolina Michalska is the PI. Here is her email address. Zoe Finfrock is a co-investigator. Georgie and I are also part of that team and playing a supportive role to help the two of them. So if you have any questions or interest in understanding it more today, and you want to talk to Georgie or me, happy to do it. But feel free to contact our leaders out there. You can write a general user proposal. You can get the support to do that at Argonne. There is beam time guaranteed for people doing BER relevant science. If you don't want to go as a general user, there's also the FICUS program. The Advanced Photon Source has keyed in through the FICUS program to do the same type of thing there with joining EMSL and JGI. And finally, there's also lots of big discussions where we'll take some of the samples in Monet and bring them to the Advanced Photon Source to do some imaging there. So that's where I will end. Thank you all for your attention. And if there is time, I'll be happy to take questions. Thanks.
Thank you, Ken. I'm just going to see if there is any question, one quick question for Ken.
So I'm not quite sure how easy it is for you to go back on your slides, but you showed some XAFS fits. And just like in small angle scattering, I see a lot of discrepancies between the observed data and the fits.
Which one do you want?
The next one, the one that you, this one, right? No, yeah, there you go. So, like, how good are these fits really? Because the shape is on the one way you say this is a lot better. I agree it is a lot better, but still not like perfect. And even for the model data, there are discrepancies between the minima. So where do these come from, and how serious is this?
I say one, it's 1 plus or minus 0.25 atoms of iron sitting there. That's the accuracy and the confidence that we have with those numbers for the data quality that we have right there. So everything that you said, that is incorporated into the error bar, if you will, to that. So when it's 1 plus or minus 0.25 atoms of iron.
Okay, yeah, I was just looking at the curves. I wasn't even looking at the numbers. So,
your point is well taken. But the discrepancies that you're seeing is what comes to bear in the error or the accuracy with which we can quote these numbers.
It's just I don't have any feeling for this whatsoever. I was just curious how to interpret this. But thank you.
Thanks for the question. Okay.
One more quick question. Thank you, great work, and thank you for sharing it with us. Can you tell us a little bit more about the makeup of those colloids, particularly when you look at their size differences?
Well, it turns out that there's really not a lot of difference in the chemical makeup of these particles at the different sizes. They're just smaller particles of the same stuff, but it's a mixture of iron oxides, maybe some small amount of clays, iron, structurally incorporated iron within clays, but very, very small fraction there. Ravi's the only one that's able to actually pick that up with his technique. And then the organic matter associated with that. And then there are small amounts, and I mean very dilute amounts of uranium and other heavy metals that would stick to these things, these nanoparticles.
Have you looked into the organic matter?
We did, unfortunately, we haven't gotten any definitive results yet. But FTIC RMS was also performed on those samples too, here at EMSL. Sorry, I don't have any more information for you yet.
Okay, if you'd join me again for thanking Ken for a great talk.
I'm Gatlin.